Did you know that the properties of triangles, rectangles, and parallelograms are used in designing bridges to make the structure strong? At the end of this lesson, you should be able to define area of a planar region, compare congruent and similar figures, identify the condition for two figures to be on the same base and between same parallels, prove parallelograms on same base and between same parallels are equal in area. Prove if a parallelogram and a triangle are on the same base and between same parallels, then area of the triangle is half the area of the parallelogram. Solve problems related to areas of parallelograms using the theorems covered. Look, Carl is working on the computer. He is doing an assignment given by his teacher. By getting familiar with the drawing tools of Paint, he draws a rectangle of length 4 cm and breadth equal to 1 cm. He then uses the copy option to copy the figure drawn and pastes the same to get another rectangle. What do you observe if you compare the shape, size, and area of the two rectangles drawn? Since the second rectangle is the copy of the first rectangle, the two figures have the same shape and size and hence are congruent to each other. The area of both the rectangles is 4 into 1, which is equal to 4 cm square. From this, we conclude that if two figures are congruent, then they must have equal areas. Suppose Carl draws a square of length 2 cm and breadth 2 cm. Then the area of the square is 4 square centimeters. Now, compare the shape, size, and area of the rectangle and square. We observe that the rectangle and the square do not have the same shape and size, but they have the same area. So, we can conclude that two figures having equal areas need not always be congruent. Now, Carl has drawn a closed boundary enclosing the rectangular shapes. A part of the plane enclosed by a simple closed figure is called a planar region, corresponding to that figure. Its area is a number associated with the part of the plane enclosed by the figure. Now Carl uses a triangular tool and draws a triangle on top of the rectangle. The figure drawn resembles the shape of a house, with rectangles 1 and 2 as windows, rectangle 3 as a door, and the triangular portion on the top acting as roof. What is the total area of the figure drawn? Since the planar region formed by the figure house H is made up of two planar regions of the roof R and the region of the front wall FW, then the area of the house is equal to the sum of the area of the roof R and the area of the front wall FW. Therefore, we can conclude that if a planar region formed by figure H is made up of two non-overlapping planar regions of figure R and FW, then area H is equal to area R plus area FW. Carl now draws the same figure again on the earlier one using the same base. Carl is not very satisfied and does the same drawings again. What difference do you observe in the first and second set of figures that Carl drew? On observing the first set of figures, we find that the two triangles ABC and DBC are on the same base BC, two parallelograms PQRS and SMN are on the same base SR, and two trapeziums ABCD and DEFC on same base DC. In the second set, we find that the figures share the same base but also have their vertices on a line which is parallel to the base. For example, for triangles ACB and DCB, the vertices A and D are on a straight line which is parallel to CB. So, we can say that both the triangles are on the same base CB and between the same parallels AD and CB. Similarly, the two parallelograms PQRS and SMNR are on the same base SR and between the same parallels SR and PN. And trapeziums ABCD and DEFC are on the same base DC and between the same parallels DC and AF. Are you curious to know where this concept is used in real life? The knowledge of parallelogram and triangle with the same base and between the same parallels is used extensively in architecture. The use of this concept enhances the load-bearing capacity of buildings. Let us do some activity on a geoboard. If I stretch a rubber band on the geoboard to form a shape of a parallelogram of base 6 units and altitude of 4 units, then what is its area? We know that area of a parallelogram ABCD is equal to base into altitude. Substituting the values of base and altitude, we get area of parallelogram ABCD is equal to 24 square units. Suppose I make another parallelogram using the same base AD, then what will be its area? Area of the parallelogram can be found by either using the formula or by counting the number of squares it endorses. To calculate area by counting the squares, we take only the count of the number of completely enclosed squares. Some more than half enclosed squares, but we ignore the partially enclosed squares of the figure. Each figure of the parallelogram has 20 square units, which are completely enclosed, 4 square units, which are enclosed more than half, to get a total of 24 square units. What do you observe on comparing the areas of the two parallelograms? The two parallelograms ABCD and AEFD have the same area. So, we conclude that parallelograms on the same base and between the same parallels are equal in area. Another way of proving this is by using the method of congruent triangles. Now, draw a parallelogram ABCD on a sheet of paper. Then, draw a line segment DE to form triangle ADE. Trace triangle ADE and place it along the other edge BC. Label the corner as F to form triangle BCF. From this activity, we find the triangle ADE is congruent to triangle BCF. Area of triangle ADE is equal to the area of triangle BCF, but area of parallelogram ABCD is equal to the sum of areas of ADE and area of parallelogram EBCD. Substituting the area of triangle ADE is equal to area of triangle BCF, we get area of parallelogram ABCD as equal to area of parallelogram EFCD. From this, we conclude that the two parallelograms are equal in area. In a triangle ADE and BCF, angle DAE is equal to angle CBF, as they form corresponding angles when AD is parallel to BC and AF is the transversal. Angle AED is equal to angle BFC, as they form corresponding angles when ED is parallel to FC and AF is the transversal. Also, angle ADE is equal to angle BCF due to the angle sum property of a triangle. Also, parallelogram ABCD, opposite sides AD is equal to BC. We know that if two angles and an included side of one triangle are equal to two angles and an included side of the other triangle, then by ASA criterion, the two triangles are congruent. So, here triangle ADE is congruent to triangle BCF. Therefore, area of triangle ADE is equal to area of triangle BCF, as congruent figures have equal areas. Now, area of parallelogram ABCD is equal to area of triangle ADE plus area of parallelogram EDCB, which is equal to area of triangle BCF plus area of parallelogram EDCB. As we can observe, this is equal to area of parallelogram EFCD. So, parallelograms ABCD and EFCD are equal in area. Suppose a triangle and a parallelogram are on the same base and between the same parallels. Then, can you find the relation that exists between their areas? To find this, let us draw a line BQ parallel to AP such that ABQP is a parallelogram. Now, ABQP and ABCD are on the same base AB and between the same parallels AB and PC. Therefore, area of parallelogram ABQP is equal to area of parallelogram ABCD. Let us consider this as equation 1. Diagonal PB divides parallelogram ABQP into two congruent triangles. Triangle PAB is congruent to triangle BQP. This means that area of triangle PAB is equal to area of triangle BQP. Consider this as equation 2. Now, area of triangle PAB is equal to half into area of parallelogram ABQP. Consider this as equation 3. From equations 1 and 3, we get the area of triangle PAB equal to half into area of parallelogram ABCD. If a triangle and a parallelogram are on the same base and between the same parallels, then the area of the triangle is equal to half the area of the parallelogram. Now, let us apply our learning to solve some practical problems. How do you find the area of triangles formed by point P in the interior of parallelogram ABCD, and what relation exists between those areas and the area of parallelogram? In parallelogram ABCD, by construction, AB is parallel to EF. Let us consider this as equation 1. AD is parallel to BC as they are opposite sides of parallelogram ABCD. AE is parallel to BF, which we can consider as equation 2. From equations 1 and 2, we get AB is parallel to EF and AE is parallel to BF. So, ABFE is a parallelogram. If a triangle and a parallelogram are on the same base and between the same parallels, then the area of the triangle is equal to half the area of the parallelogram. Triangle APB and parallelogram ABFE are lying on the same base and between the same parallels AB and EF. So, area of triangle APB is equal to half the area of parallelogram ABFE. Consider this as equation 3. Similarly, triangle PDC and parallelogram DEFC are lying on the same base and between same parallels CD and EF. So, area of triangle PCD is equal to half the area of parallelogram EFCD. Consider this as equation 4. Adding equations 3 and 4, we get area of triangle APB plus area of triangle PCD is equal to area of parallelogram ABCD. Let this be equation 5. In a parallelogram ABCD, by construction, MN is parallel to AD. Let this be equation 6. AB is parallel to DC as they are opposite sides of the parallelogram. AM is parallel to DN. Let this be equation 7. From equations 6 and 7, we find that MN is parallel to AD and AM is parallel to DN. If a triangle and a parallelogram are on the same base and between the same parallels, then the area of the triangle is equal to half the area of the parallelogram. So, quadrilateral AMND is a parallelogram. Triangle APD and parallelogram AMND lie on the same side of AD and between same parallel lines AD and MN. So, area of triangle APD is half the area of parallelogram AMND. Let this be equation 8. Similarly, triangle PCB and parallelogram MNCB are lying on the same base and between same parallels MN and BC. So, area of triangle PCB is half the area of parallelogram MNCB. Let this be equation 9. So, area of triangle APD plus area of triangle PCB is equal to half the area of parallelogram ABCD. Let this be equation 10. Comparing equations 5 and 10, we obtain area of triangle APD plus area of triangle PBC is equal to area of triangle APB plus area of triangle PCD. If P is a position on the interior of a parallelogram ABCD, then area of triangle APB plus area of triangle PCD is equal to half area of parallelogram ABCD, and area of triangle APD plus area of triangle PBC is equal to area of triangle APB plus area of triangle PCD. A farmer had a field in the form of a parallelogram PQRS. He took a point A on RS and joined it to points P and Q. Can you count the number of parts the field is divided into? What are the shapes of these parts? From the figure, it can be observed that point A divides the field into three parts, which are triangular in shape, namely triangle PSA, PAQ, and QRA. We observe from the figure that the area of parallelogram field is the sum of triangular regions PSA, PAQ, and QRA respectively. Consider this as equation 1. We know that if a parallelogram and a triangle are on the same base and between the same parallels, then the area of the triangle is half the area of the parallelogram. So, area of triangle PAQ is equal to half the area of parallelogram PQRS. Let this be equation 2. From equations 1 and 2, we get area of triangle PSA plus area of triangle QRA is equal to half into area of parallelogram PQRS. If the farmer wants to sow wheat and pulses in equal portions of the field separately, then how should he do it? Observing the above equation, we can conclude that the farmer must sow wheat in triangular part PAQ and pulses in the other two triangular parts PSA and QRA. Or he can sow wheat in triangular parts PSA and QRA and pulses in triangular part PAQ.